representative.
This is the sort of thing that we have to do now to find out if we're properly sampling and if we can control our operation with quality control, and we can do that. We have to do that, particularly if we're making a lot of one material. But what do we take as that little index that we're going to measure? Now with you this morning, I took as the index that I was going to measure the number of times that it took to break the paper clip, right? Is that a fair index to judge the material by? Well, what we would really like to do is to inspect a material so that we can get an index that did not cause us to damage the material. You broke the paper clip. I can't find out how many times I can bend a paper clip and still use it as a paper clip if you broke it in two, right? So we cannot have a destructive type testing. We're going to have a non-destructive type testing. And so it behooves us to, in this business of looking at our materials and service, see how we can enable ourselves to inspect a material, to examine a material, to find out its worth, find out its capability of being used, its serviceability. And I would like to now go through a series of tests that we use, or talk about a series of tests that we use, and you can see some of the problems that we have. The first test I'd like to talk about is an old one, a very old one. Actually, it is in, if you look your history up, you find out that Lord Nelson used this one back in the Admiralty, the British Navy, in examining anchor chains. And being an old Navy man myself, I can vouch for the fact it's a good system, because I once upon a time back in the 30s used to have to do this myself. And what happens is that you may get a crack in an anchor chain. And if you get a crack in an anchor chain, it doesn't respond the same way that it would respond if it were a whole anchor chain if you hit it with a hammer. If that doesn't sound right to you, just think about the Liberty Bell, right? I mean, they rang the Liberty Bell, sounded all right until it cracked, and then it gives off a false indication. So if you pull up the anchor chain and take the stress off of it and hit it with a hammer, it'll ring like a bell. And the next anchor chain, next link will ring like a bell. And finally you hit one, it goes flonk, and you say, something is wrong with this anchor chain, this link. And that was an inspection method that was used. And so we find that actually Lord Nelson's little technique of doing this was pretty good, but he had a better method also that's still used today. And in this particular method, it's called a dyed penetrant method, and this is the way Lord Nelson would practice it, or the way they practiced it when I was a boy. You would have a crack in an anchor chain link, or a crack in anything, say a bar that I suspect of having a crack in it, but I can't see the crack with my naked eye, because these cracks are microscopically small. One of the things I could do is to take a dye, let's say an oil, like any lightweight oil that has a dye in it, like cochineal bug dye or something like that, red number 2, I don't care, anything that would dissolve in the oil to make it red. And I scrub it over or immerse the part in the oil, making sure that if there's any crack there, that the oil has a time to, by capillary seepage, get in the crack. And then I very carefully wipe all of the oil off of this particular part. And then I whitewash it. Now whitewash is just calcium carbonate, very fine particulate matter, in water. But water and oil don't mix. And so there's going to be no red color that's going to come out and mess up my little paint job, my whitewash job. So I can whitewash the anchor chain or the bar or whatever I have, hang it out to dry, and when it gets rid of the water, and we have left now this powdery material which will absorb oil, right? The limestone will absorb the oil, and by capillary seepage the oil comes back out of the hole, and since it's dyed red, then on this beautiful, brilliant white piece, I see a little mark that says, hey, underneath this you got a crack, and it's this particular shape. Well, sounds pretty neat. Today we do the same thing. We don't go to all of that trouble. What we do is we use a fluorescent dye, in, say, in a carrier, an oil carrier. We spray it on the part. It still penetrates the crack. We wipe it off real good and put it under ultraviolet light, and gee, it lights right up for us, and we can tell where the crack is. And that's called a dye-penetrant method of inspection. If we have a crack, this is a non-destructive method of determining that we have a crack. If you had a lot of material that you're going to inspect, does that mean that you would throw the whole lot away? Not necessarily, not if these sort of defects are repairable. Because you'd put it in line and say, if you can repair this, if you can chip out the crack and weld it back up or make it sound, then it's okay. This is not a cause to reject the whole thing if it's repairable. If it's not repairable, then you say, maybe I've got a lot more in there that are like that. Well, this is a non-destructive technique, even though we have a crack in it, because we could repair it. But suppose the crack doesn't come to the surface. What then? Well, one of the things we can do is we can X-ray it. We can radiograph the material. It's just like if they want to know something about your lungs, they radiograph you. And it depends upon the relative density of the material in the path of the X-rays, and the X-rays will go straight through you. And so if you have a mass in your lungs or in your body that's of a different density, then you won't get as many X-rays through, and so on a film it will be a light spot, and they can tell that you have something there. Now we can do the same thing with a crack. If we shoot an X-ray beam through a piece of metal that has a crack in it, then we are going to say if the path that has metal in it is decreased, that is to say if we have this opening, which we call a crack, then the X-rays passing through this now are going to be more abundant than they would be anywhere else, and on the X-ray film we would see a dark spot, and it would delineate the crack. Sounds nice and foolproof, but it is not foolproof, because if the crack is situated in the material so that we look at, let's say, a flat type crack with the X-ray beam coming in perpendicular to the crack, then the path difference between, in the solid metal, between the material that's sound and the material that has the crack is not very great, because we didn't leave out much metal, since the crack is going to be microscopically small. So it almost says, hey, we need either to X-ray it from several different positions, several different directions, or we have to have some a priori knowledge about what the shape of the crack is before we can start delineating it with the X-ray or the radiography. But this is a nice technique, and there's obviously a limit on the size of the crack that we can detect, because if the crack is very, very small in length, may still be a crack, and even if we look at it along the length, so the path differential would be great, we may not see it because the crack is so small. So X-rays or the radiographic technique is not foolproof, but it's certainly one way to look at cracks. Another way that we could look at the crack to find out if there's something in the material that's going to bother us now is to do magnetic particle inspection. Actually, this will work for cracks that are on the surface and cracks that are slightly below the surface. In this particular case, let's suppose that we have a crack that's on the surface, and let's suppose I have just a handheld magnet for the moment. We have devices where we can put big magnetic fields across a piece that's in, particular one that's in manufacturing, that we just put it in a machine and we develop a magnetic field to sit the material in. Or in the field we can take, say, a welding machine and wrap a cord around the particular, say, ferrous material that we have, and we can set up a magnetic core with a DC current in this. We have a big magnetic field. But in reality, all you need is a horseshoe magnet with a little spread between the points, and say we can put it on a ferromagnetic material. We could have something as simple as a powder sprayer, a duster, if you please, something that you may spray dust onto your flowers with. And in this dust, we're going to put magnetic particles, let's say magnetite particles, iron oxide that's ground very, very fine, and may even have some talcum powder mixed with it to make it easier to see. We put a magnetic field across this piece of iron, and then we spray the powder on it. Well, just as with a magnet, if you put it on, let's say, under a sheet of paper so you can't see the magnet, and you sprinkle iron filings on the outside, you find that the iron filings cluster at the poles of the magnet, at the end of the magnet. Then you have in your piece a crack, and that means you have ends of the material. And so around those ends, the magnetic particles will cluster. And so you can just look at it and you find that you spray the material on, it falls off, or you blow it off, except it won't be blown off where the magnet is holding the particle on. And even though that crack is slightly under the surface, it will be delineated. And it's called magnetical particle inspection. Is it foolproof? The answer is no, it's not foolproof, because the crack may be too far under the surface for you to see.
An early non-destructive evaluation technique for inspecting anchor chain for cracks involved striking each link and listening for a ringing sound, meaning that the link was good. While today's dye penetration techniques are more reliable and easier and faster to perform, they rely on the same principles of early testing, where a dye reveals cracks by seeping into the crack via capillary action. X-ray or radiography relies on relative density to reveal subsurface cracks and other defects. Magnetic particle inspection finds surface and near-surface discontinuities of ferromagnetic materials.
Well, there are other methods of doing this, and we do the same sort of thing electrically by a technique that's called electrical impedance method, or the eddy current method. And in this particular case, we are going to induce electric current into the piece. And that says we are going to put in the piece a field that is generated because it's next to a current flowing in a wire. And since we do that, if we move this particular little coil that we have a generation of a back EMF, and we have this impedance that we can measure on an instrument. We can find out that there's a little blip right there. If you took such a coil and you ran it across the crack, then you would find that as you ran it across the crack, you'd get a jump in the needle. Or if you have earphones and you can listen to the noise that's produced, you find that you get a squeal when you cross the crack. Is it foolproof? The answer is no. If the crack is too far inside, then we can't make the field be generated down into the material. We won't feel the impedance back in the coil, and we may miss it. Well, is there some method that we can use that we'd have a little bit more confidence in? And the answer is yes, there is. And this particular method involves ultrasonics. Now, we did a little bit of ultrasonics in the courses this week, and what we did was, remember, I said the tin will talk to you, right? And we bent the tin, and it twinned, and it said something. Acoustically, we heard the material plastically deform. This is called acoustic emission. Well, a question that you should have asked me, or you should have thought about, was, look, if I can hear it twin, could I hear it slip? Or if I bend the material and it cracks, actually breaks on the inside, and it neither slips nor twins, but it fractures, could I hear it crack? And the answer is, yes, we can hear it crack. Can we hear it slip? Well, there are a lot of people in the field that say you can. I'm not really sure. I've tried. I haven't heard it yet. But I presume if you had an instrument sensitive enough, you ought to be able to hear it slip. If you have motion in time, or movement, displacement in time, then you ought to make a noise. If you have a device that's sensitive enough to pick it up, you could hear it. Well, we have devices like that, and they're called piezoelectric crystals. We're back to crystals again. You can't get away from crystals in this field. But a good piezoelectric crystal, let's say, is quartz, been known for a long time. Now, piezoelectric crystal is a crystal, always a highly anisotropic crystal, but it's one which, if you squeeze, it will generate an electric current. Or if you provide an electric current across the crystal, it will change its shape. And that says that if we have a piece of quartz of the proper cut and the proper thickness, the proper orientation, the proper thickness, and we put an electrical